Okay, so we've actually made it to the last day. Woohoo! Yeah. We've made it to the last day. Thanks for sticking with it this long. I wanted to throw up here, I forgot to put this on Piazza, I was going to. Listen, has anybody in here a TA right now for a different class? Positive or negative or medium experience? Positive, okay, lots of positive experiences. If you want to be a TA, and you should go to this website, www.cs.tufts.edu/tilde/mole/compta, and you have to fill in a little form, and you talk about your grades and what classes you've taken and so forth. We choose the TAs for the next semester right about the week and a half before the semester starts, so you wouldn't hear anything about that. Now, this is a tough semester because most of the people who are currently TAing are going to want to continue TAing, so there won't be many spots open. So don't be upset if you don't get a TA spot this semester. Generally, I look for people who did very well in the class. Obviously, A's are a good thing when it comes down to this. And I know most of you guys now, so I think personality figures into it in the sense that I hope you can I hope you work well with other students and so forth, and just kind of seeing how you've done. So that's kind of how we make those decisions. So if you want to do that, great. I think it's a positive experience because you continue to learn many more things being a TA. All of the TAs for Comp 15 this semester had to learn at least some Eclipse, whether they wanted to or not, right? And so yeah, so you will learn something new as a TA, and you'll just keep practicing things. So that's good. Let's see. As far as the project goes, hopefully you guys saw. If you didn't, then this will be a very good moment for you. But hopefully you saw that that I extended it till tomorrow night, the project. If you, I would rather not give any other extensions because I think that's probably generous enough, and we have to start grading it and so forth. What else was I going to say about that? Somebody wrote me a feedback on the anonymous feedback, and I replied to you. If you happen to be in this class and I replied to you and you didn't get it, it's because for whatever reason that thing doesn't email you back saying you've got a return email. So go back on and check. What else? Anybody have any last minute questions on the project? Yes.
Oh, no project.
On anything else?
Were you going to send out a list of who wants to?
Oh yeah, you mean as far as the midterm? Yeah, I have to put something. I'll put something on Piazza. It might be like a poll or something that just says, look, if you're going to go to the other section, check yes or something like that. You can. I'm not going to stop anybody from doing it, but I just want to get a feel for how many. But I haven't done that yet.
Are there sections?
There's 2 final exam dates. One is Friday, this Friday, and the next one is the following Wednesday, and you can go to either one.
What's the time? That it was this Wednesday.
3:30 for both, I believe. Yeah. Not in this room either. It's in a different. It's in Robinson 253, which is a bigger room. You'll be able to spread out a little bit, not much, but a little bit. Okay. All right. Any other questions on the project or anything else? Please look at Trunk. If I screwed up your grade so far, you need to tell me or I won't know. And I'd rather not do it after you get your grade and say, why did I get this grade? It doesn't make sense. So let's try to handle all those issues before the mid-year or the final. Okay? All right, I'll have some other comments at the end as well. Let's get into the final review. So today we're just going to go over the things that I think you should take a look at again for the final. The one thing that I actually forgot on here that I don't believe I asked you a try question on the mid-year. I don't think there were any try questions. I may do that. So even though tries aren't on here, you might want to go back and review tries as well. But we'll talk about AVL trees, which are probably so far back in your memory, you're like, oh, I don't even remember anything about that. So we'll try to do a little review there. We'll talk about heaps. We will go back over sorting a little bit, just the basic stuff. You guys hammered away with the sorting on homework 4, so I'm not too worried about those things. And then hash tables, and many of you are hammering away on hash tables now, so you'll probably do fine there. And then we'll talk about graphs, and I can tell you right now, you'll see Dijkstra's algorithm on the final, so make sure you study. The best thing to study would probably be that piece of paper I handed out a couple weeks ago where we all did it in class. If you don't know, I think that piece of paper is still online in the lecture for that day. So yeah, you can go and look at that. We'll go over Dijkstra's one more time today. And then just a little bit on the esoteric stuff just to make sure that we cover that just a little bit. Nothing too extreme on that. Okay, it looks to be like there's going to be more programming, writing out programming than there was on the previous one. But I'll try to make it so that it's still a reasonable length. Hopefully you won't be here more than 2 hours. Yeah.
Will we be getting like a practice or a past exam so we can kind of...
I'm not going to give out the past exam, although I guess it doesn't really matter. It's going to be completely different than last year's, but I wasn't planning on it. Maybe I'll reconsider. I don't know. We'll see. But I can't guarantee it. And then finally, we will do a recap of the first day's results. I wanted to go back to the first day and show you what I showed you then, and you guys will be hopefully pleasantly surprised at how much you now understand about what I threw up there on the first day when you're like, oh, I don't know what's going on, and then now you'll understand the whole thing. Okay? All right. AVL trees. All right. So let's just review AVL trees. Remember, AVL trees are a way of balancing a binary search tree. Okay, so it is a binary search tree. It has to follow binary search tree invariance, which is what? What do we know about a binary search tree? Nathan. Left child is always less than the parent, and the right child is always greater than the parent throughout the entire tree. That defines a binary search tree. AVL is a binary search tree that happens to be balanced such that the balance condition differs no more than 1 in any of your subtrees. So you go to a node, if you count up the height difference, or the height of both subtrees, if it differs by more than 1, it is not AVL compliant, and therefore you have to make it AVL compliant by doing this balancing stuff. Okay? Remember that stuff? Yeah, Maretta?
And we start from the leaves to go up and find the first one that's not...
Right. You start from the leaf, and in general, you'll, as far as I know, although, again, I've read differing opinions of this, but as far as I know, you'll only have to balance once, no matter where you insert. If it's already an AVL tree, and then you insert something, you only have to balance once, whether it's a single or a double rotation, and then you're done. I don't think you need to do, and you do it from the lowest one. You'll be good. Okay. All right. So remember, because of the way we do this balancing, there's 4 different categories of balancing we have to worry about. Okay. The first is if you insert if you're checking on the heights, and you find that the first node that's out of balance, okay, you would have had to have inserted somewhere in one of its subtrees. If you inserted in the left subtree of the left child, that's only a single rotation. If you insert into the right subtree of the left child, we're going to go over these. We're going to see some examples of these. It's a double rotation, which is a little trickier, but once you get it, it's not hard at all. And then there's the exact opposite, which is the left subtree of the right child or the right subtree of the right child. Okay? If it's the same direction, you only have to do a single rotation. If it's the opposite direction, you're going to have to rotate twice. And we'll show how to do that. Questions on that? Okay. All right. So in this tree up here, okay, it's at 7, and then 3, and then 9 is the next level, 1, 6 the next level under the 3, and then 5, and then 4 under the 6, and then 8 under the 9. Which node is the first one that's unbalanced? Figure it out. Going from the farthest one down. Well, let's start from the bottom. Is the 4 unbalanced? No, it has no children, so it can't be. How about the 5? The 5 is not unbalanced because the left is 1 and the right is 0, and that's not unbalanced. It differs by only 1. How about the 6? Okay, the 6 is now unbalanced because it's got a left subtree of a height 2 and a right subtree of a height 0. Okay, so we got to do some balancing here. Okay. So 6 is the one that's the first unbalanced one. How do we balance it? How do we figure this out, Ben?
Well, should I just give it straight away?
Go ahead and tell me how you figured it out. Yeah.
Take the 5 in the center, and put it where the 6 is.
Okay, hold on. Before you even do that, why do you know that you're only going to have to rotate one? Because you're only going to have to rotate once, like a single rotation. But how do we know that? Which category does it fit in? That was really my question. Which of these four categories? Left subtree, left child, right subtree, left child, etc. It's the which child, left child, and in which one did 4 go into? The left subtree. So left subtree, left child means there's one single rotation. That's what it means. Okay, we'll do the other case in a second. All right, so you take the 5. Now, my little trick to do this, or my way to remember it, is you take the 5 and you do what? Shake it out, and you hold the 5 and you go whoop and start pulling it up. The 6 goes to the right of 5, and the 4 stays on the left of 5, and then that's it, right? So we're going to do a single rotation, and it's called, technically it's called a left rotation, I'm sorry, a right rotation of 6, because 6 is rotating to the right. How do you rotate 6 to the right? You grab 5 and hold it up and do it. Okay, grab 5 and shake, and it ends up like that. Now, are we balanced? Everybody seems pretty balanced, right? 7 is balanced because it's 1, 2, and 1, 2, 3. And 3 is balanced because it's 1, 2, and 1. And everybody else is balanced. OK. So that's one case. Now, there is a very similar case like this, except look what happened. And I had to manipulate which numbers were where anyway. But I inserted the 5. So what's the first one that's unbalanced? Still 6. And how is this different? Yeah, because now it's the left child, it's the right child of the left subtree. Or is it the right subtree of the left child? Thank you. The right subtree of the left child. Right? So that's the opposite ones. And if you tried to balance this by taking 4 and shaking it up, the 6 and the 5 both end up on the right of 4, and you can't do it. So what you need to do is you need to say, fine, rotate 4 left, even though it doesn't seem to make sense. But to rotate 4 left, which one do we grab? 5, and we shake 5 on one level, and the 4 goes to the left, and then it goes 6, 5, 4, like that, All right, it goes 6, 5, 4, like that. Now we've got a left-left situation, which it happens to be exactly the same as the situation before. And now we can rotate 6 right. So that's what a double rotation is. OK? You have to be able to differentiate this and then draw this. I'm not going to make you code how to do this. It would take many pages of code to do this. Not a fun one to code. But just understanding it is the tricky battle, the battle here, winning the battle. OK? So then we grab 5 and shake it, and now it comes back to actually the exact same result as before. Yenny.
Go back to where it was like before.
Like this. So what's wrong? It was a right subtree of the left child. Did I say that one right this time? Yep. Yeah. And then you have to, because of that, you have to do this double rotation. Now, if you look at the online thing, there's kind of a sneaky way to do it, right? You can look up at 3 and go and grab 5 directly and shake like that way. You can shake 5 2 levels up, and it tends to work, but it's a little harder to conceptualize. I just like that. Hey, get it so that it's a left-left. How do you do that? Rotate 4 left, and then rotate the 6 right, and you're done.
So what was the intermediate step?
The intermediate step was you have to rotate 4 to the left, which doesn't seem like it's possible, but when you do that, you grab onto 5 and you shake it, and it goes like that. And then you rotate 6 to the right, which means you grab 5 again, and it ends up like that. OK? All right, be able to do that, you'll be good to go. OK? All right. Any other questions on AVL trees? I know it was a while ago. OK. Let's talk a little bit about heaps. Now this is fair game for programming, like to actually writing out code, right? If you should know backwards and forwards how to write the code for heaps. I would go look at your lab for that, right? Your heap lab, where you had to do it, at least for a couple of them. Okay? Why do we care about heaps? We use them for a priority queue, right? We use them for a priority queue, and they tend to have better performance than any of the other types of priority queues we can think of, like an ordered list or an unordered list. And what's nice about heaps is there's not an ordering per se, but you can always pick off the minimum or the maximum, which is exactly what you want in a priority queue. And we can turn it into a heap sort, which is also fast. So that's nice. OK? All right. By the way, I'm not in particular stressing asymptotic behavior for any of this stuff, but you do need to know all of your asymptotic behaviors like we've talked about in class. That you should not forget. Two types of heaps, right? There's a min heap and a max heap, right? The min heap is where the minimum value is at the top, and the min invariant is what? What's the invariant for a heap? A min heap. Invariant for a min heap. Maggie?
The parent is, for a min heap, the parent's smaller than the children.
Right. For a min heap, the parent is smaller. You can always just say that in any heap, the parent is higher priority, whether higher priority is less or greater, depending on how you mention it. Okay? And that's it. Meaning that the exact same heap here, if this was 5 and then the 10 and the 8 were swapped, it would still be a heap. Right? Because there's no independent ordering. You can't walk through a heap in any order. Which is why some of you you can if you just do remove min, but you actually have to remove min, rebalance or reheapify it, and then and go from there. Okay? All right, let's see. Remember that heaps are binary, they're complete binary trees, which means that they go all the way, they keep filling in on the left as far as they can until the last level where there might be some empty ones. Okay, what's nice about this way of ordering it, or knowing that heaps are this way? We can store them how? In an array, right? Much easier to store in an array than an actual tree. And we store it in an array. Normally we just kind of ignore the 0th element. It makes the math a little bit easier. The math isn't so bad. Left child of an element is 2 times the element index. The right child is 2 times the element index plus 1. The parent is just divide the element index by 2. It's the floor of that. It's the integer division. The heap size is the number of the elements in the heap, etc. Okay? Yeah.
If we were coding this on an exam, can we assume that we can use the floor function, all of that stuff?
Can you assume the floor function? If you would just assume division, that does a floor function. Integer division automatically does that. Yeah. It just means that it 7 divided by 3 would be 3.5 in real life, right? But it's actually 3 because it just truncates the fraction part. Okay? Did I do that right? 7 divided by 2, thank you, is 3. 7 divided by 3 is 2, yeah. Right. I'm losing it. I got off a plane at 6 a.m. from Seattle. I'm going to claim that as my argument, my excuse. Okay. That's that. Let's see. So here's one example. So you should be able to code up remove min. You should be able to code up insert, which basically means you're going to have to be able to code the 2 functions for upheaping and downheaping, right? So you should be able to do those. But again, look at the lab. You should be good to go on there. Okay. I might ask you to do something like this, where I say perform the remove min and show the resulting heap, and then maybe explain how you do that. Give me the resulting heap after you do a remove min, and then say there are 3 steps. Step 1 is take the min and you're going to return it. Step 2, replace the element 1 with the element at heap size, etc. You see? Decrement the heap size. So just step through it like that. Yeah, Aaron?
What should we expect to happen? Should we just, for these, for AVL and for heaps both, should we expect just to have to know how to visualize and perform them, or should we know also how to code them?
AVL, you don't have to know how to code. This you do.
Okay.
Yeah, heaps you do. Okay. All right. Any questions on that? Heaps are a fun data structure. I like them. They're kind of cool. Okay. Let's see what else. Describe the procedure to add a new element, and then I might say add 6 to the heap. Right? How would we add 6 to this heap? Where would it go, first of all? Maggie?
It would go to the right of 43.
It would go right. It would go to the left child of 11, which is at heap size plus 1 in this case. Okay. And then what would we do?
And then you bubble up, so you look at 6 is less than 11.
Yep. So 6 would be here. It's less than 11, so it would go here, and 11 would go here, and then.
And then if it's less than 10.
Less than 10, so
switch.
So 6 goes here, and 10 goes here, and then this one.
And then
Check against 5. So it ends up being 5, 6, 10, 11, and that's it. And we've inserted 6, and it's still a heap, and we're happy. Good. Know how to do that. Know how to code it too, but definitely know how to explain it. Yep.
So the textbook talks about an just like comparing like to use blanks and like keep it as a blank and go up? Do you care which way we do it? It's like it was like, oh, instead of swapping, keep a blank and compare, and then only swap the ones you need to.
I don't remember that, but if it works, then, and it still is considered upheap, then sure. Yeah, if you can explain it. If you started saying blanks and stuff, I might not know what you're talking about. And I can almost guarantee the grader doesn't know what you're talking about. So try to use the terms we use in class. Try to do it about like that. All right. Okay, anything else on heaps? Okay, so sorting. We did tons of stuff on sorting, right? We talked about all these different types of sort. Insertion sort, selection sort, heap sort, shell sort, merge sort, quick sort, radix sort. I've seen a ton of people using their insertion sort almost directly from their sorting homework. That's awesome. Okay. Selection sort, you probably shouldn't do that. What's the one case, I've talked to a couple of you about this. There's one case where selection sort is actually a pretty good sort to use in certain situations. Any ideas? Certain situations is very key. Like there's only one real situation where selection sort would be helpful. Alex, what do you think?
If you're dealing with like an extremely small list, like one, two,
Even if you're small list, we would rather use insertion sort. What do you think?
If you just want to sort like a few of the elements.
Yeah.
And then
Yeah, if you just want, like, let's say you have a list of 1 million elements, and you just want the top 10, right? Insertion sort, you're going to have to do the whole thing before you're guaranteed that the top 10 is in the first 10 spots, right? For a selection sort, after 10 iterations, you've got the top 10 in the right place. So it's not that fast for those top 10, but if you're only doing a certain top number, you can get them relatively quickly. It's better than any of the other sorts, really, in terms of doing that. Because it's basically saying, fine, where's the first element? Where's the second element? Where's the third? You know, and that's what it's doing. But that's better than any other real overall algorithm for this. So yeah. So there's cases where you do that. And hopefully, if you learn anything from this class, it's that these either corner cases or special cases, if you think through these things, some of these algorithms are better than others in lots of in certain situations. So hopefully you kind of got that idea from this class. Okay? So you should be able to describe the algorithm for each type of these sort. I won't make you write a sorting algorithm, but I might make you sort some, like I might give you an array and say, perform quick sort on this, right? And how would I do that? I'd have other arrays, and so it's hard to grade that, by the way. But I would want you to perform. I might want you to perform the algorithm to sort something like this. So quick sort's a good one. I guess any of those are pretty good. I'd probably, well, even shell sort. I mean, that one wouldn't be too bad, right? It would not be more than like 5 or 6 elements. So I wouldn't want you to take forever to do it. Okay? But you might have to do that. Okay? And explain the complexity, best and worst. Don't worry about shell sort. That's the weird one. You should be able to explain some of these other complexities. Okay? All right, what else about sorts? Well, most of the sorts we talked about were these comparison sorts. At some point in the other in the algorithm, you're comparing two numbers together and saying, which one's bigger? Right? That's a comparison sort. The one that we talked about that's not a comparison sort is a radix sort, which doesn't work that way at all. There's never a comparison between two numbers, which is why it's tough to compare radix sort to quick sort or radix sort to merge sort, because they just work fundamentally differently. So even though you might be able to say, look, radix sort is the number of digits is order, the number of digits times the maximum, times the, what is it? That's m times n. Is that what it, or d times m? So you have to, it's the number, the length of the number of maximum digits times the, yes?
It's 2 times the number of digits you have to sort through.
I don't think it's 2 times.
Because you have to,
But
you have to put it into your queues and then dequeues them.
right, but you have to do that how many times? You have to do it by the length of the maximum number, the number of digits in the maximum number. Yeah. So anyway, you should be able to talk about that. I'm not going to ask you to compare these directly, except maybe to say, you know, which would be faster, an insertion sort with this type of arrangement or a quick sort with this type of arrangement, something like that. Okay? The best a comparison sort can do is n log n. Some of you guys didn't know that in your, when we asked you those questions on your homework grading. Speaking of which, if you haven't gotten homework 4 graded yet, you have to email me. Because right now you don't have a grade. And for whatever reason, you didn't link up with a TA, and you need to talk to me about that. Okay?
You mean five, right?
5, sorry, thank you. The sorting one, not the other one, sorry.
Are we supposed to see a grade on trunk if we have met with the
No, I haven't put any grades up yet. But if you've met with a TA, then you're fine. I'll send emails if I don't hear from people in the next couple days. There's only about 15 of you, something like that, the whole class. Okay. So sorting we can do in place with you can't normally do it exactly in place. You're always going to have 1 or 2 elements extra, but you can do things generally in place. We like those because it doesn't take all this extra space. And if we're sorting huge numbers of elements, we don't want to have twice that amount or 3 times that amount of space, or log n times the amount of that space, right? So things like merge sort, which are hard to do in place, even though they're fast, are not necessarily the ones we're going to use because they take up all this extra space. So you have to consider that. Okay? And then there's other sorts that, by virtue of what you're doing with them, say recursion or so forth, have all this overhead that it means they're not that effective for sorting small problems. This is why most implementations of sort, when you get down to only 5 to 10 elements, will just have an insertion sort for the rest of it. It's just faster to do insertion sort for 5 or 10 elements than it is to take all the extra overhead of doing a quick sort. Okay? All right, questions on sorting? Here's the kind of things I might give you. Describe the quick sort algorithm. Explain why divide and conquer algorithms get to log n behavior, and log n in particular for the sort. Okay, you're dividing in half, half, half. That's by definition logarithmic. And then demonstrate. So you might want to demonstrate how to merge 2 already sorted arrays. Pretty easy. And like I said, you might have to perform 1 or a bunch of iterations on a particular sort so that I know you know how to do it. Okay. Any other questions on those? All right. Hash tables. So we're getting to closer to current times, right? So hash tables, remember, hashing produces a number, and it can be from a string, like you're maybe using in this project, or it can be another number that gets hashed to a particular number. But in the end, you get a number which gives you the bucket location, right? And that bucket location is probably modded for the table size that you're using. Okay? You use that bucket number and you say, here's the index of where this is supposed to go, and then you plonk down your data in that position. Right? Lookup in this case is great. You just hash it. That doesn't take much time at all in general. And then you go immediately to the index value, and we've gotten this holy grail of asymptotic behavior where it's constant time. What's the problem with hash tables this way? There can be collisions, right? It sounds so great until you realize there can be collisions, right? So yeah, we can get if we have no collisions, you can have perfect behavior, but most of the time there will be collisions. Remember, there's that birthday problem issue where there's a 95% chance of at least one collision if you have a 1,000,000 sized array and only 2,000 hash values. 95% of the time you will get at least one collision. So you can't ignore collisions. You have to be able to deal with them. Okay? And of course, there's lots of ways of dealing with collisions, right? First way we talked about was this chaining idea, linked list. Anybody end up using chaining for any of their collisions? I know a couple people did. Is it fast enough? Yeah, it's pretty fast when you don't have them when they're not that long and you keep the load factor small. Okay? So you can do these. This is where you have you don't necessarily have to change the bucket size. Do you expand the table though?
Yes.
Yeah. Expanding the table with a linked list is a little hairy, but you can do it. In this case, so you just, when you get to a bucket and there's other stuff there, you just add it onto the linked list. You don't need to find a new bucket. Like, that's the fast part. You just say, fine, it's there. Right? You do want to expand it if your load factor gets too high, but you don't have to. You could have a 5-element, you could have a 1-element hash table and have it chained, and it would just be a linked list. Right? That's really it. But it's so that's a nice benefit of it. The downside is, well, look, you're having to add another data structure to your data structure, which is not necessarily the easiest thing to conceptualize, or for that matter, program correctly. Okay? And it can, of course, degrade into linked list behavior if you aren't careful about it. Okay? All right. How else did we deal with collisions? Well, we have these linear probes. Who are using linear probes for their? Yeah, most people are, right? This one's not a bad one. It's there's nothing particularly bad about it. If you have a nice hash function, linear probing is generally fine because you're not going to get these groups of hashes. Okay? It's easy. When you have a collision, you just start walking to the right in the array until you get to a place there's no spot or there's nothing there, and just drop it in. Okay? It's simple. That's one of the benefits. There's no extra data structures, right? Downsides are that when there's groups of hashes, you can significantly slow down the probe if you happen to have a bad hash function. The other downside I didn't put on here is that you have to expand, right? There's no way about getting around it. If you don't expand, your program will just spin forever when the table is full, because it'll just go around and around and around. And unless you've figured out how to say, oh, I went through the whole table already, then you're in trouble. Okay? But it's easy. All right, there's a couple other types of collision. This is, by the way, called open addressing for collision handling. And there's quadratic probing, which says instead of going x plus 1, x plus 2, x plus 3, you do like x plus some number squared, or like 2 and then 3, some n squared, like your attempt squared. Okay, and then you end up jumping farther in the table. Yeah.
So when you don't know what you're going to be receiving, what makes that more logical than just doing it linear?
Yeah, that's a good question. I mean, I think people use this one when they think there might be groups of hashes in their table and they want to jump a far distance away.
Oh.
That's really it. Yeah. Benefits are, of course, if there are groups, then you will jump past them and you won't have to worry about that. The downside is you have to be a little bit careful when you expand, because if you choose this, there might be a case where you skip, and then always skip certain values, and they never get filled, and then your load factor is kind of off, and you're wasting space, and not so great. Okay, there's probably some way of proving whether or not you are going to be in that situation. I just don't know how to do it. Okay. All right, and then there's a double hash. This is just another way of doing it. You say, okay, look, we hashed to begin with to a certain bucket. That bucket's filled. Let's hash to another bucket as well. Like take that hash and rehash it to another bucket. Okay, and then that will step forward in weird kind of ways. It won't be linear or in a direction at all. Yeah.
Will that, like, if that new bucket already has something, does it rehash the original hash function?
Generally, you just keep rehashing the second hash function. That's kind of the way I've seen it done before. Yeah.
The way we did it was like the second hash function, instead of hashing the key, it hashed the number of attempts, and then we just added.
Oh yeah, it hashed the number of attempts and added it. So yeah, it's using another hash on the attempt. Yeah. So just another way of doing it. Okay. All right. Again, downside, you want to watch out for skips, and it's a little more challenging to program, but not particularly. Okay. Let's see. I talk about expanding. I didn't mention yet. When you're finding the value, and this actually, some people had a bunch of questions on Piazza about this. Look, when you're finding the value, you basically do the exact same thing again, like this stepping through, until you get to a place where you either found the value or it's empty. And if it's empty, that's not in the hash table. And if you found the value, obviously it is. Okay? What two things do you need to store in the hash table at that point? You definitely have to store what? The key as well as the data, right? So that you can do that comparison and see if you're at the right place. So that's, you got to remember to do that. Okay, we mentioned load factor a little bit. The load factor just says how full is my table? And it's just a fraction. It's the number of keys you've stored divided by the total amount of space you have. And you use that to determine whether or not you want to expand. Okay? And it's generally a floating point number, which confused some people too, as far as how do you get the floating point number out of two integers being divided. But you have to cast it to a float. Okay? All right. If you do keep a low enough load factor, you end up with more or less constant behavior, which is what we're looking for, which is why we can do searches fast enough. Okay. All right. How do we expand the hash table? This is a tricky one. I could ask you to write a little expand function for a hash table. Probably won't, but I could. when you get above a certain load factor, you have to do this expanding, and you can't just copy all the values. You'd love to be able to do that, but when you copy all those values, what happens? You lose them, right? They're not hashed in the same bucket anymore, and so they're gone. So that would be bad. That would be bad news. You have to rehash all the values. So you have to go through all of them again. So rehashing is a slow process, kind of by definition. All right? It's not tremendously slow, but it's slower than just copying them. Okay? But you have to do it, and the fact that you have to expand every so often does outweigh the fact that the load factor is slow. Right? It's the same idea. You're always doubling the size, so you don't have to expand that often. It's slow when you do, but eventually you get to a point where you don't have to do it often, just because it's an exponential growth. Okay? All right. We did talk briefly about cryptographic hashing. Okay, cryptographic hashing was this idea where you have these one-way hash functions, and it makes privacy, the ability to have privacy in communications, the ability to have secure communications, the ability to prove that somebody was the originator of a message, or something like that, right? We use it a lot of times. Passwords gets hashed, signatures, electronic commerce, all these things rely on these hashes. Okay, if you want, there's a cryptography class being taught. I believe it's next fall. So if you've taken, let's see, what would you really need to take this class? If you've taken discrete mathematics, Comp 40 you'll probably have taken by then if you're a CS major. It's good to take 160 before it, which is the theory of computation, but you may not have a chance if you want to take it next fall. But if you are kind of mathy, it's not a bad class to take at all. And it's also taught by the best professor in the history of Tufts and probably universities in the world. So that's good. It's Professor Hescott, who's awesome. OK, so that's that. Just have to know about that. There's nothing I'm going to ask you to program for cryptographic hashes. You might just need to talk about it. Okay? There are some things like you might need to come up with these. Right? Easy to compute a hash value, but it's hard to generate a message that has a hash. Right? Infeasible to modify a message without changing the hash. Remember, we want to have two messages that are really similar. If we hash them, they come up with totally different hashes. So you have no idea that my password's hello and Yenny's is hello1. Right? Okay. It's infeasible to modify a message without changing the hash. In other words, you can't change like one or two things and change and leave the hash the same. And it's also difficult to find two different messages that have the same hash, which means that you can pretty much rely on your hash being unique. Okay? Yes?
Sometimes emails get hacked and the hacking changes your email, so and you still get messages. How does that work?
Sometimes emails get hacked and they still... Well, right. So most messages, believe it or not, are not hashed with any cryptographic hashing. This is actually kind of a problem. Like if you use Gmail, Gmail has said that they're going to start, well, I think they've started already. So if you see the little HTTPS in front of the name of the email client, it's probably going to be encrypted. But most email is not encrypted. Like your Tufts email, I don't know that it's encrypted. It basically goes plain over the internet. Right? So it's relatively easy to hack some of that stuff. Yeah. Which sometimes you'll get an email, it's like from a friend. Have you ever gotten this email that says, you know, it says, hey, I'm stuck in London and somebody stole my wallet and I need cash. Have you ever gotten that email? And it's like from a friend of yours. Like, oh my God, you got, you know, this. And then you look at it a little more closely and you're like, yeah, I don't think that's even proper English. I don't think my friend would do that. Then you email them and they're like, no, I didn't write that. But that's because there's something was hacked in there. Probably just the email address. Who had a question in the back there? Ready? Yeah, Logan.
Isn't a lot of like backbone email, like the emails between servers, not encrypted at all?
Right, it's generally not. Right, the email between servers is generally not encrypted at all. Yeah. What if you have the HTTPS? It generally means that like from here to the Gmail server, it's encrypted. Right? Gmail unencrypts all your mail, so they can get all your they can read your mail and see what kind of ads they should send you. Right? So they know that you want to buy new tennis sneakers or something. I don't know, and they'll send you ads for that, right? But in the meantime, in the middle, I think Gmail is encrypted. But I'm not sure Tufts email is. Yeah. It's if you ever want to get a little bit scared about how networks and things work, download a program called Wireshark. And what it is it listens for anybody's wireless communications. Like, so Alex is on his computer back here, and right now his computer is sending messages back and forth. And if he's not on Tufts Secure, he happens to be just on Tufts Wireless, I could have Wireshark here and capture everything he's sending to anywhere. Just like that, right? Just by using this program called Wireshark.
That's also how
Yeah.
people reverse engineer mobile apps. So for example,
Yeah.
if there's like I know that's how a lot of people originally before Tinder was like had like a security team. People used the messages it was sending back and forth to figure out API keys, and then like
Figure out who it was and all.
figure out who it was, and then they were able to swipe right on themselves from other people's accounts.
Oh, great. Great. Well, anyway, so the point is that, like, I know all you guys are like, hey, just use the Tufts Wireless. If you use Tufts Wireless, I'm telling you, every time you like do a search or anything else, it goes unencrypted into the world. Google generally encrypted these days in general, but most of the other stuff is unencrypted. Your email is unencrypted, and I could capture them, which is kind of scary. Yeah.
So if you're using like the different APIs for like Facebook and things like that, and you have to get the person's permission to like use their things, and it gives you like an access token.
Yeah.
Is that access token really like like a public key sort of thing? So you use
Yeah, if you're using the public, so you're talking about like COMP20 kind of stuff. If you're using a public API, you generally get a hash value, which is that key you're talking about, and that's only good for one use generally. It's not good forever. It's just good for one use, which you could do a lot with it probably, but not too much. They've got the back-end security pretty tight now, but it is hackable in the big scheme of things. So anyway, all right. Cryptographic hashing, that's about it for that. What kinds of stuff could I ask you? I could say, here's a hash function and a table size of 9. Hash these values, right? This would not be a hard problem, right? Let's do it. We might as well, right? Hash equals the number mod 9 with a table size of 9. 0, 1, 2, 3, 4, 5, 6, 7, 8. Hash table size of 9. Hash the following keys. Create 2 tables, chaining, and then linear probing. OK, where would 5 go in this? 5. So let's do this with chaining first. So I'm just going to say it goes to 5. And then where would 29 go? 29 is 2, right? So that's here. 29. And then what? Let's see. We've got 20. Also 2. OK. And then 0. 0. And 27. 0. And 18. 0 as well. And there you go. OK, that's that one. Let's do the same thing with linear probing. 0, 1, 2, 3, 4, 5, 6, 7, 8. OK, linear probing. OK, so we go with 5 goes in 5 again. So it goes right there. OK, and then 29 we said goes in 2. OK, 29. And then 20 also goes in 2. So we go to 2 and we go, nope, it's got to go there. Into 3. And then 20. Sorry, that's 20. That was so 0 goes in 0. And then 27 also goes in 0. So it can't go in 0. It's got to go in 1. OK, now our table's getting really full. And then 18 also goes in 0. Nope, 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 nope. There it is. So there's your hash tables. Right? And if we want to find 18, we go, OK, it should go in 0. OK, well, that's not it. There's something there, 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 that's it, that is it. And so we found it. So you see how that works? OK? Let's see if we can come up with one that's not in there. What if we did 4? Right? 4 hashes to 4. So we check this is not there. It's not there. It's not there, but that's empty, so it's not in the table. Pretty easy. Right? OK. All right, so that's how we would do that. Same thing, you could go through the same idea here. It's even easier with chaining. OK. All right. Let's see. Write the insert function for a hash table that uses quadratic probing. Could I ask you that? explain how an element should be deleted in a hash table that uses chaining and how it should be deleted in a hash table that uses open addressing. This you kind of have to make a call, right? With open addressing, you have to say, oh, how do I actually delete 20? Well, 20 was going to go in a 2, so I have to go find it, and then I can delete it. But if there's other ones, what's one way of dealing with it? Well, you could rehash. You mean everybody? Yeah, you could do that. That is one way. It's not a very particularly great one. Yeah, Mateo.
Boolean that starts as false and gets set to true and element put in there.
Yeah, you could have another little piece that says false or true, and then you could do it. And there's other ways of making it compact later and so forth. Yeah. Good. Nathan?
I would rehash, is this linear probing table?
Linear probing, yeah.
So yeah, what I would do is I would rehash the one that's next to it to the right, and continue doing that until you find something that does not hash to the spot that you deleted. So now you've got the last one.
Oh, I see. So you're you're rehashing until you get to a place where it doesn't go in there. But I guess but yeah, see, the problem with that is, go ahead, what were you going to say, Maggie?
Yeah, well, I was going to say that you kind of like inserted, like if you inserted something that hashed to 4, say like you inserted like 5 things that hashed to there, but then you inserted some stuff that hashed to 5 and then to 4 again. Like you might
Yeah.
run into.
You might have trouble with that. You'd have to, I think in order to do that properly, Nathan, you'd have to rehash the whole thing.
Or you could go all the way to an empty slot instead of going
But
to the
if
slot
you
of
had like
something else.
deleted stuff.
You just go to the empty slot, and then the last one, the most rightmost one that passes to the one that you.
I guess so. It sounds pretty intense, but I guess you could probably work it out so that you wouldn't do it. But I think having a Boolean value there that says, hey, this is deleted, is probably the easiest way. Maybe not the most efficient, but definitely the easiest way. OK, good. All right, we are on to graphs. So graphs, remember, I said this in lab and in class a couple times. Graphs are they're like trees in the Wild West, right? They have no structure necessarily to them, right? They've got nodes, which we call vertices, and they've got edges, which connect them to any other vertex in the entire graph. Okay? You've got a couple different types. You've got directed and undirected. The directed ones have arrows, which means they're only adjacent in one direction. They're not adjacent in the other direction. So if 11 points to 9, and there's no arrow back from 9 to 11, you can't directly go from 9 to 11, but you could go from 11 to 9. Okay? Remember, graphs also have weights associated with them. If it doesn't have weights, like if there's no numbers in there at all, we generally just consider that a weight of 1 or just a true-false type value for the thing. Okay? We talked about a couple of different shortest path algorithms. I'm going to just review those really quickly here. Okay, one was for unweighted graphs, and the other was for weighted graphs. We also talked about the algorithm for weighted graphs that had negatives in them, that either were or weren't cycles. I'm not going to make you do anything specific with that. I might ask you about cost cycles and negative cost cycles, but I'm not going to ask you to do an algorithm based on that. Okay? All right. So with an unweighted shortest path algorithm, well, what do? You pick a start vertex, right? And then you find the shortest path to all the other vertices from that start by doing the following. You mark the path from the first one to some other, or the first one is 0. Then you go and mark the ones that are 1 away from it. And then you go and for the new ones, you mark the next ones by adding 1 to your current weight. Okay, I know it's a lot of like words, but I'll show it to you in a sec. And you keep repeating until the nodes have a minimum distance. Okay, so here it is right here. So if we have an unweighted graph and we start at vertex 3, right? It's got 2 vertices that it connects to, 6 and 1, and this is a directed one. And so you immediately go to 1 and 6 and mark them as 1, and you mark 3 as completed, right? And then you pick one of the next ones, it doesn't matter which one, and you do the same thing. You go to the ones that it's adjacent to and add 1 to its value, right? So if I pick vertex 1, I say, fine, it's to 2 is just another 1, and to 4 is another 1, etc. Okay? And then we do the same thing, continue with the same thing. Okay? This is just a breadth first search, if you didn't realize that. Okay? Because you're just going to go out in that direction. You should know the difference between breadth first and depth first for graphs. Yep.
For an algorithm like this, or the other ones we're going to do, would we be labeling like on a graph, in a chart? Would we be
You'd be labeling in a table, kind of like the one I did for Dijkstra's algorithm.
So it would
Yeah.
be more like visually, not coding, but like visually saying what goes
Yeah.
where.
Yeah, visually saying what goes where. It's if you practice the Dijkstra one, you should be good to go, right? Okay. All right. So this is the type of table you might have to fill in, but I'd probably have it like I did before, where it's a table that goes sideways, like a spreadsheet sort of table. Okay. And we check all these as known and so forth. Okay. And we can have some infinite paths as well. If you can't get to a node, you have an infinite path there. Okay. All right. Then, of course, we have Dijkstra's algorithm. Now, we did go over this a number of times in class, so I'm not gonna spend too much time on it. But basically, remember, this is a greedy algorithm that says at every stage, I'm just going to do the best I can right now based on the unknown nodes, whichever one has the least distance now. I'm going to go to that one and try to keep going in the direction that I need to. Okay, it's a greedy algorithm. So each stage just decides whether it needs to go down that path or not. Okay, we have these charts, and again, the one that I might make fill out is going to be like sideways here, so you're going to be filling in these as you go. Okay, updating like the previous and updating the distance as you go. And let's just walk through this one. I think this is the same exact one we did before, right? If we start at vertex 1, right, we mark down vertex 1 has a distance of 0, and then we can go and choose the adjacent vertices there and mark their distances. So 2 has distance of 2 and 4 has distance of 1, and we mark down that they both came from vertex 1. Then we keep going. We now select v4. The reason we selected v4 was because it was the one that was, of the unknowns, it was the one with the least distance. So you have to choose this one. If there's ties, you get to choose. Like you to pick based on whatever you want. But if there's no ties, you have to pick the one that's the least. So you do 4, and you keep going. You mark 4 as known, and then because we're doing 4, we get to go 5 and 7 and 6 and 3, and mark all of those, and we update those with the addition of their weight plus the current weight for that vertex, and make sure you mark where the previous one was. And then you continue to do 2, because it's of the unknowns, it's the least. All right. You don't change the ones that are already known, nor do you change any that would go back to a higher value. Okay. And then we select, here's a tie, so we could select either 5 or 3. Okay, let's select 3. And you don't change 6, even though 3 is adjacent to 6. You don't change it because it would be adding 5, which is more than what 6 already is. Okay, you don't change it to 9 in this case. And then you don't change 1 because it's already known. So you guys get the algorithm here. We've done it a couple times. Okay.
Why was that a tie? Wasn't V3 already true?
No, not right now. There wasn't.
Oh, okay.
And then boom, now it's true when I'm doing it. Okay, and you just keep going with this. All right, keep going, keep going, keep going, and you printing out the at the end, printing out the shortest path is just a recursive algorithm going backwards. So if we want to print the shortest path to 7, we go, okay, comes from 4, 4 comes from 1, so we had to go from 1 to 4 to 7. Recursive. Okay, you will see this a ton. All right, other kinds of questions I could ask you about Dijkstra's algorithm. What types of applications in real life use it? Right, lots of different ones. Ben, what do you? Navigation systems is the big one. Communication systems, right?
Yeah,
Networking.
Wireless network.
Wireless networking. Yep, all those things use these things to make sure that you're doing shortest paths. Yes.
So on the lab that we did on graphs,
Yeah.
depth first search is basically an implementation of Dijkstra's algorithm, right?
Well, the depth first search, remember those were unweighted, I believe, too. So it wasn't really Dijkstra, it was more the unweighted algorithm, right? And that was more the breadth first one, was this one we kind of showed you here. But yeah, that wasn't necessarily the shortest path either. That was just a path, right? Like it was a search, so saying, hey, I'm going to try to find this. And the searches aren't necessarily minimum, right? This is trying to find every path to every other node. right? A search would be like, hey, is this one in the graph? Let's do a depth first search. Dot, dot, dot. Oh, I found it. I haven't found it yet. You know, and then eventually you find it. Okay, good. All right. Yes?
Can you have a node that is not connected to or from any other nodes? Is that legal in a graph?
Is that legal in a graph? I believe to be part of the graph, it has to have one adjacent vertex to it, but to some other part. But maybe not.
They can be isolated.
They can be isolated? Yeah, I don't see why they couldn't be.
Graph theory.
Yeah, graph theory, they can be isolated, sure. Yeah.
Can be
I guess if you're on Facebook and you have no friends,
Well, my point is that
then you're
wouldn't,
Yeah.
like searching for it by going like.
you can't search. There's nowhere to search, right? I mean, you'd still have it. Let's say it's in the table. It would just never. You'd never get there or have anything to go to from it. So yeah, you could, but yeah. Okay, cool. All right, so that's Dijkstra's algorithm. Here's some more questions. So I might ask you to complete an adjacency matrix or an adjacency list or a visual graph, right, based on one of those. I might ask you to say, hey, give me a breadth first or a depth first traversal, kind of like what you did in lab. I could definitely say find the shortest path. I will almost certainly ask you to apply Dijkstra's algorithm. Okay? Questions on that? All right, that's graphs. And then finally, the last things we talked about were the esoteric data structures. Now, I'm not going to ask you really in-depth questions about these. I just want you to know them to the extent that you can describe them a little bit. I'm not going to ask you to program anything. For instance, skip lists, I could say, hey, describe how to insert into a skip list where you flip a coin, and if the coin comes up heads, you insert into the next level up. And then you flip a coin again, and if it comes up heads, you insert into the next level up. And when it comes tails, you stop inserting. That sort of thing. Okay, I might say, what's the asymptotic behavior of a complete perfect skip list? And you'd go, oh, it's 2 times the log n. Or even if you just said log n, I'd probably be happy. Okay. Bloom filters. Bloom filters were this other probabilistic data structure where it can have these weird false positives, where you can say, is this in the filter or in the set? And it says probably when it's not necessarily there. Right? It can't say it's not in the set if it's not there. That's the nice thing about Bloom filters. But if it is, it can't say that it's not. No.
Right.
Did I say it backwards?
If it's not, then you can't say that it's not.
Oh, right. if it is in there, if it is in there, it can't say that it's not there. Yes. Okay. Right. And if it does say that it's not, you know that it's not in there. That's probably what I meant to say. All right. Okay, so that's Bloom filters. Pretty cool data structure. Again, these are the kinds of things you want to throw out at your interviews to impress them. Don't do it wrong, though. Don't say, yeah, I'd use a Bloom filter for that. And you go, no, you don't want to do that. You know. Yeah, exactly. Sorting algorithms. Yeah, I'd use a rope to sort things. No, probably wouldn't do that. Ropes. I kind of want you to know the trade-offs between ropes and strings. Why do you, what's good about a rope? You can insert right in a spot in logarithmic time. Nice. And then we briefly talked for one day about binary decision diagrams. Just be able to basically walk a binary decision diagram and tell me what the solution to a Boolean function is, whether it's 1 or 0. Okay? I don't want to make you spend time trying to do that whole figure out the binary decision diagram. It's just not worth it. Okay? Esoteric data structures. Any other questions on that? Okay, so that is really the stuff we've covered since the mid-year. I suggest for studying purposes, looking at these slides again and making sure you understand what I'm expecting of you there. I would go back to all the labs you've done since the mid-year and review the code, because I could ask you to write some code. I will ask you to write some code, and you might as well review it. Okay, I know that's hard to do, but you might as well review it. Francesca, and then
I know that most of the solutions are out for the labs, but not all.
I think all but maybe the last one. So I will post, if you just send me a quick email, I'll remember to post the last one. Yep. Yanni?
Should we order queues and stacks and stuff too, or will they come up?
So here, again, your study plan, I would do that last. I would look at where queues and stacks last. I don't want to focus on those because there's so much from the mid-year that we haven't talked about on a test. It just doesn't make sense. But I don't want you to lose all that. Yeah? No, you don't have to write copy constructors or operator assignment overloads. No. Good question. Sorry for putting you through that pain. All right. Okay, so that's that. Yeah. You can have a cheat sheet. Let's leave it as one back and front page. Okay, so you can't bring your old one in, but if you want to bring your old one in, it might not help you as much. But if you want to copy some pertinent stuff from that, go ahead.
So,
Yeah.
so the back and front of the sheet of like normal 8 by 11.
Normal 8.5 by 11. Yeah. Normal 8.5 by 11. Handwritten. Don't type it in micro font. Handwritten by a human. I don't know. This robot has a hand. I don't know. Okay.
Oh, yeah.
Yeah.
Oh, I remember something very pertinent from last time, for the midterm, was, oh yeah, tree search orders, binary tree search orders.
Binary tree search orders? I don't know what you mean.
Or level order.
Level order? What about level order?
Oh, shit.
You have to know level order. I mean, you should know how to traverse a...
Pre-order, post-order.
Yeah, you should know how to do those. Yeah. But most of that was covered on the mid-year. Okay, any other questions on the mid-year? Remember, Robinson 253 at 3:30 either Friday or next Wednesday. If you can't make either, I don't know why you couldn't make either unless you made plans already. Somebody said they already made plans. They couldn't make either for some reason. Email me and we'll figure it out. Okay? All right. So I wanted to finish up by going back and saying, do you remember day one in this class, right? Now, day one, we talked about a whole bunch. We talked about logistics. We talked about the class itself, kind of big ideas. But I also gave you 4 structures, and I put up a table that I'm going to refresh your memory with in a second, where I said, we've got this dynamic array and then this linked list. And I said, you don't have to know what that is, even though most of you already did. And then I said, there's this hash table, and you all went, a what? Hash table? And then a binary search tree, and you went, I've never heard of that, right? And I put those up, and I put some data associated with doing a few different things to those structures, right? I believe it's on here. Here's what we did. We took 100,000 elements, and we added them to each container, to a dynamic array, to a linked list, a hash table, and a binary search tree. Okay? And then it searched for 50,000 of those. Okay? So it put the even integers between 0 and 200,000, and then it searched for 0 to 50,000. So half the searches came up not found. Okay? And then we deleted 20,000 of those elements. Okay? And then I put it into a table, and I said, look at the differences here, right? And I said, hang on, the hash table is going to be kind of a cool, important one eventually, and you can see why from day one, right? But now you guys know why it's so great, right? Because everything's constant behavior, right? The binary search tree is pretty darn good. Arrays, not so great. Linked lists, terrible, right? Linked lists are just not a good structure for a lot of things. Okay? Maybe I should have done a skip list too. And then sorted array, the sorted array was pretty good overall, but the inserts were really slow. And now you guys know why, right? And of course the searches were fast. What kind of search can we do on a sorted array? A binary search, yeah. What kind of delete was I doing for the hash table? I believe I was just marking it, like as deleted. Yeah, I think that's what I did. Because I believe I did write a hash table for that one. I think I wrote all these functions. The binary search tree was actually what it's called a red-black tree, which you will learn about if you take algorithms class. You'll do it in depth. It's similar to an AVL tree where there's rotations and things, but it involves, you basically mark some nodes as being either red or black nodes, and then you deal with them rotation-wise based on their color. Yeah?
Did you have to expand your hash table?
I did. Yep. I had to expand the hash table. Yep. OK, so what I did a couple nights ago, took a while, was I said, what if we had 10 times more elements? Instead of 100,000, there was 1,000,000. And the same exact things. Look at the differences here. Linked list took an hour plus to do this, right? I just let it go, and I'll come back later. And I came back, and it was an hour later where that one was finally done. Right? Searches on a linked list are terrible. All right? Now, here's a question for you. If there's 10 times as many elements, what was the asymptotic behavior of a linked list? For searching, let's say. Linear, right? So if there's 10 times as many elements, how much longer should it take? 10 times as much. Now, it went from 23 seconds to 3,600 seconds. That's not 10 times as much. But what else is going on here? No, not deletions. Good idea, though. What else is going on? It took me a second to figure it out, too, because I went, wait a minute, did I do something really wrong with this linked list? And then it turns out I didn't. Yeah.
Not always reaching the end of
No, not always. No, it has something that's fundamental to the problem that I did. I did 1 million more elements. And so I had to do, I not only 1 million more elements, I also did 1 million search, or 500,000 searches instead of 50,000 searches, right? So I had 10 times as many elements, and then I did 10 times as many searches. So what's the time going to be? 100 times different on the order of, which it really is, right? It went from 23 to 3,600. That's on the order of 100 times difference. Okay, so you can see some of the same behavior there. Okay, but notice something about this. Look, our little hash table is awesome, right? For 1 million elements, it's like, yeah, whatever, bring it on, right? It doesn't care, right? The binary tree was pretty good too. Sorted array, not so good. Linked list, terrible. Array, not like terrible. So now you get why this is why we care about these things. Okay, I made homework server crank away for 2 hours on this. Yeah.
What was your load factor like for that?
I'll have to look, but I believe the load factor was, I want to say load factor was on the order of 0.5 or 6 or 7, right around there. 0.5, 0.6, something like that, yeah. Yeah. But remember, you're amortizing this over, 1 million times. It only has to expand. What does 2 to the what mean equals 1 million, right? 2 to the 20, something like that. So it only had to expand 20 times for all of those, So out of 1 million searches, not too bad, or 1 million inserts. So here's some more data on this, yeah?
Is there a way to take through load factor versus just I know for the project we just did, I just tested it a bunch and saw
Yeah.
which one.
No.
Is there some formula that if your data is this and
There might be some heuristic value. That would probably make a pretty good paper, actually, if you want to figure that out. But most people end up picking it by empirically, where they test things. And for most, for random data, it's generally around 0.7. I think Java uses 0.7 in their hash table. I think so, yeah. So here's some comparisons directly, right? For the arrays, again, linear, right? 9.8 to 935, about 100 times difference, because 10 times more times 10 times as many searches, right? Linked list, we said that was terrible. Hash table, right? Look at that. That was 100 times difference. So I mean, that was, or is it 10 or is it 100? 10 times difference, right? Because it's constant times 10 times as many searches. Right? So boom. Okay? A little bit more than 10 times for binary search tree, not bad. Sorted array, a lot more because the searches were so terrible, right? Or rather, because the inserts were so terrible. On sorted array, you got to, as you're inserting, you have to keep it sorted, which you guys know. So it was terrible. All right? Inserts in general were not so bad because most times inserts are fast in almost all our structures. Right? Even the linked list was fast in that case. But that's not where it's the searches that kill you on the linked list. Okay? And the sorted array searches were really fast. But of course, because you're doing a binary, you're basically doing the same thing as the binary search tree. So it's even more efficient. Why is it faster than the binary search tree? There's more overhead to a binary search tree, right? You have to traverse nodes and stuff. With a sorted array, you go immediately to that index. Right? There's no traversing, really. Yeah. I mean, I think that's probably the biggest difference there. And my solution is probably not that efficient. But that's that. OK, so you see how much we've learned a lot in this semester, I hope, in the sense that you look back at this and you go, OK, I get it. Now I know why hash tables are so efficient, and now I know why a sorted array takes so long to insert into it, et cetera. OK? Yeah?
Why is the search for the hash table, why is it so different if you're keeping the same load factor?
Good question. Anybody have any ideas? I'm not exactly sure, but I would guess that it probably has something to do with the fact that it probably has something to do with the fact that you're still having to do a bunch of traversals. Like when you find, you search the location, you're still going to have to do the traversals, even though you're right. If the collision or if the load factor was decent, then it shouldn't be. But it's not going to be perfect. It's not going to be constant, even if it should be close to constant. But yeah, good question. I do 10 times as many searches. That's a good point. So, yeah, you're right. So it's a little bit off, but not, yeah.
Yeah.
Good call. Anybody else on this stuff? Okay, so we didn't cover a lot of these things. Actually, funny, this is like the same little chart I used last year. We did cover one of these. We covered skip lists. But there's a million data structures out there. If you go to the Wikipedia page, there are a ton of data structures out there. I have no idea what a spaghetti stack is, but it sounds cool. Right? It's probably used for something somewhere, and it makes sense to use it for that. What's that?
Like you can't really make a spaghetti stack.
Well, I don't know if you can make a spaghetti stack. It depends what a spaghetti stack is, right?
Oh, no, you create a spaghetti heap. We all know.
We hear a spaghetti heap, right? Exactly. Thank you. A spaghetti heap, right? But there's lots of these things, right? Rolling hashes. I don't know what those are, right? Radix trees. So there are a ton of algorithms. All of these build on the things you already know now. Okay.
I found what a spaghetti stack is.
What's a spaghetti stack? Huh?
It's also called a cactus stack.
Okay.
And child nodes have pointers to parents' nodes, but not the other way around. You need to go search it like you're searching a linked list.
So it's like an upside down tree or something?
Kind of. But it runs like a linked list.
It's like the parents have disowned the children. And,
Why is that
You don't have one.
why is it useful? That's a good question.
Doesn't say.
Yeah. Yeah.
You don't have one. You have a whole.
Yeah, I'm not sure why. Yeah, not sure why that would be useful. But yeah. So my point with this is saying, look, we didn't cover a lot. Obviously, we didn't cover every data structure. That's impossible. But we covered enough so that you have a good ground truth for going ahead to other classes. Okay, this really is a fundamental class in computer science for a reason, right? And because it's fundamental, that's why Google and Microsoft and all those people ask you questions based on all of this stuff, right? Because they want to know if you know the basics, because everything else builds on this stuff. Comp40 will build on this stuff. Some of the other programming languages, you will certainly talk about these, or classes rather, you will talk about these sorts of things in all your other classes in some form or another. Comp20, you probably talked about certain things that you went, oh yeah, we learned about that in data structures, I'm guessing. Yeah, so that's that. Okay, now, first of all, you guys are awesome. Thanks. I have been really impressed by how hard all of you guys have worked. Most of you guys. I mean, look, there's some people who haven't worked hard. I know that, but most of you guys have worked very hard, and I appreciate that. I think every day, I think tough students work harder than most other places I've ever been. So, congratulations on getting through this. I think you guys did a great job. Hopefully, you'll do fine on the mid-year on the final, and I did enjoy having this class. So, thank you very much. Thank you. Thanks, guys. Any last minute questions? See you guys at the final.